Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying functions lecture 7 and we'll be talking about different types of functions in this lecture. So let's begin our lecture with the identical functions and we'll be discussing these 3 points to define identical functions. Okay. So first point and second point are very obvious. Domain of both functions should be equal and range of both functions should be equal. That is very obvious, right? But when these 2 points are true, we can never be sure that those two functions are identical functions, right? We have to have this third point to make sure that those two functions are identical function. The third point says that both functions should have equal values for same values in the common domain. What do we mean by that? Let's say we have two functions mod x and x square, right? In this case domain is r, right? And in this case domain is also r, right? In this case range is close 0 to infinity open, right? Over here also range is 0 to infinity open bracket at infinity and close bracket at 0, right? So both domain and range are same for both the functions, but are these two functions identical? No, they are not. Why? Because let's say if I take x equals to 2 over here, in that case y would come out to be 2 in this case and y would come out to be 4. So for corresponding points, for corresponding common points in domain, we're not having corresponding common points in range, right? Range is same, domain is same, but if we take one value of domain, then that would give us different kind of output for both these functions. So that's why these two functions are not identical. So third point becomes very important when we are defining identical functions, right? Now let's see certain examples. Let's say we have x square by x and x. Now this looks like x only, but here's the catch. Here domain is r minus 0. Why? Because it cannot be 0. It is in the denominator, it cannot be 0. That's why domain is r minus 0. But in this case, domain is r. So based on this, we can say that these two functions are not identical, right? Now let's take one more example. We have tan x and 1 upon cot x. Okay. Now at first instance, it would look like, okay, these two are same, right? Because we have used them interchangeably a lot of times right from our 10th class, right? We haven't questioned that. But these two actually in general are not identical. Okay. Why? Let's see that. Let's take a point 0. Is tan x defined at x equals to 0? Yes, it's defined. So it's defined at x equals to 0. But is cot x defined at x equals to 0? It's not, right? So if cot x is not defined at 0, so 1 by cot x is also not defined at 0, right? So this is defined at 0, this is not defined at 0. So how can they be identical? They're not identical, right? So in general, they're not identical. When we have used them interchangeably, we have assumed that we are only considering those points where both of these are defined, right? So that's why we have used them interchangeably, but in general, they're not identical. Okay. Now let's take one more interesting example. What do we have? We have 1 upon sine x and cosec x, right? We again have used them interchangeably a lot of times, but are they identical? Yes, in this case they are. Why? Because we know that sine x equals to 0 for x equals to n pi, right? So basically for x equals to n pi, 1 upon sine x is not defined, right? Similarly for cosec x as well, for x equals to n pi, cosec x is not defined, right? So in that case, these two are actually identical. Now let's talk about 1 and 1 functions. So we have this set A, set B, set A and set B. Let's define two functions over here. First one looks like this one and second one looks like this one. Okay. So what is happening over here? In this first function, we have all these images having one single pre-image. All these images in set B are having one single pre-image in set A, right? But in this case, what is happening? We have certain images having multiple pre-images in set A. We have images in set B having multiple images in set A. We do have this case as well, but we also have this case where one image is having multiple pre-images in set A. What do we mean by that? In this case, these are outputs. This set B is output, right? So we have singular outputs for singular value of inputs, right? We cannot have multiple inputs for a single output. But over here, what is happening? We have multiple inputs. We have these multiple inputs for one single output, right? Although we do have this case as well, but still we have this case as well where we have multiple inputs for a singular output. Okay. So this one is called as many one function and this is called as one function. Okay. So let's take one example. Let's say we have x and modulus x. Now in case of x, what is happening? Graph looks like this one. No matter how many values we take in y, This is, let's say, 2, 3, 4. So we'll be getting exactly one input value of x, right? For all the values of y, we'll be getting just one single value of x as an input, right? But in case of modulus, what is happening? We have this modulus graph, and let's say this value is 1. So for this value 1, we have -1 and 1. Basically, we're having two inputs, -1 and 1 for this value of 1. For value of 2, we have two inputs, that is -2 and 2, right? So for one single value of y, we are having two values of x, two values of input x, right? So that's why this is a many one function and this is a one function. Okay. Now let's talk about onto and into functions. Again, we have set A, set B, set A, set B, and let's define the same kind of functions which we defined back in one and many one, but different really over here. Okay. So we have this function and we have this function. Okay. Now in this case, in the first case, what is happening? All these elements of set B have been mapped. All elements of set B have been mapped. But in case of second function, only this one and this one has been mapped. Okay. So what's the difference? In first case, codomain is 1, 2, 3. In first case, codomain is 1, 2, 3. And similarly, in second case as well, codomain is 1, 2, 3. But in first case, range is 1, 2, 3. And in second case, range is 1 and 3. Okay. In first case, codomain was 1, 2, 3. Also, range was 1, 2, 3. In second case, codomain is 1, 2, 3. But range is only 1, 3. Right. So in this case, range equals to codomain. In this case, range is not equals to codomain. So when range equals to codomain, we say that the function is onto function. When range is not equals to codomain, we say that the function is into function. Okay. We will get to know why are we defining these functions later on, but as of now, let's just focus on the definition of these functions. Okay. Now let's take one example. We have modulus x. Okay. So fx equals to modulus x, and f is defined from r to 0 to infinity. This is our codomain, right? And now if we talk about range of modulus x, you can see that it's starting from 0 and going till positive infinity. So range is 0 to infinity, right? Now we can see that range is same as codomain. So that's why this function is onto function. But you can see that it totally depends on the definition of codomain. In case codomain was defined as R, right? The function was defined from R to R, where R is codomain. In this case, the function would become into. Okay. So it totally depends on the definition of function and definition of codomain, based on which we can choose if the function is onto or into, right? And now let us move forward with horizontal and vertical line test. So horizontal line test is used for identifying if the function is one or many one. Let's say, for example, we have modulus x over here. Okay. And if we draw a horizontal line which is parallel to x-axis, we can see that it is cutting at 2 points. What are these 2 points? If we take the x values for these points, we'll see that for two values of x, we are having one single value of y. Let's say this is -1, this is 1, so this is 1, right? So horizontal line test is used to identify if the function is many one or one. Okay. If it is cutting at multiple points, you can say that the function is many one, otherwise it's a one function. And what about this vertical line test? Vertical line test is a test which is used to identify if the relation is just a relation or it's a function, right? Let's say we have y square equals to 4ax as a curve. Now if we draw this curve over here, it looks like this one. Okay. Now if I draw a vertical line over here, we can see that for one value of x, let's say this is x equals to a. So for one value of x, we're having multiple values of y. This is y1 and y2, right? For one value of a, for one value of x, we're having multiple values of y. That is y1 and y2. That means it's not a function, it's just a relation. Okay. Now what about trigonometric functions? Trigonometric functions, let's say sine x. It looks like this one. If I draw a horizontal line over here, we can see that it's cutting at multiple points. So that's why all trigonometric functions are many one functions. Okay. Unless they are defined in a particular domain, generally all trigonometric functions are many one functions. Okay. And similarly, all periodic functions are also many one functions. Let's take an example like this one. So this function is a periodic function. Okay, if I draw a horizontal line over here, you can see that it's cutting at multiple points, and it's pretty obvious, right? Because it's periodic, it's going to repeat itself again and again. So if we draw a horizontal line over here, then we can see that it's cutting at multiple points. So that's why all periodic functions are many-one functions. And now let's talk about this nomenclature, which you cannot evade because eventually you'll have to remember these terms. Okay. So one functions are called as injective functions, onto functions are called as surjective functions, and functions which are both one and onto are called as bijective functions. Okay. So you have to remember these terms. And now let's solve this question. Let f r to r be defined by function fx equals to x plus under root x square. Then f is injective, surjective, bijective, none of these. Okay. So we have fx equals to x plus mod x. Why mod x? Because under root x square equals to mod x. We know that under root has to be positive always, right? That's why this comes out to be mod x. So we have this function. Now we have to open up this modulus, right? So fx equals to x plus x or x minus x plus x when x is greater than equals to 0, and x minus x when x is less than 0, right? So eventually it becomes 2x and 0. Now if you plot it, 2x would look like this one and 0 would look like this one. Okay, so this is our function. Now we can see that this is not a one function, this is a many-one function, right? Because for all these values we have same value as 0, so that's why it's a many-one function. So it's not injective. If we talk about surjective, here codomain is R. We have defined codomain as R, but we can see that range over here is 0 to infinity, right? It's not going beyond 0 on the negative side. It's 0 to infinity as range. So range is not equals to codomain, that's why it's not surjective. So if it's not injective and surjective, it's not bijective, right? So D is the correct answer. And now let's talk about graphical interpretation of odd and even functions. So for even functions, we can say that these functions are symmetric about y-axis, and for odd functions, we can say that these functions are symmetric about origin. So what do we mean by that? Let's see. Let's take an example for the even function. We have y equals to x square over here. It looks like this one, right? Now, if I place a mirror over here on the y-axis, you can say that this right hand side is an exact replica, or you can say it's mirror image of left hand side, right? So when this happens and vice versa happens, we can say that these functions are symmetric about y-axis, and that's why they are even functions. Okay. Now what do we mean by symmetric about origin? So let's take an example of y equals to x cube over here. Okay, we have y equals to x cube. That is an odd function. If I take this origin point over here, if I travel distance d1 over here and find a point, and again if I travel backwards same distance d1 and still find a point, in that case we say that this function is symmetric about origin. Now if that is happening for all the points and all the distances, that means the function is an odd function. Okay, so if I take one more point, one more direction, one more point over here, and then do the exact opposite of over there and still find a point, we can say that the function is symmetric about origin, right? So today's lecture was till here only, and we'll be solving examples of these types of functions in the next lecture. So let's meet in the next lecture. Thanks for watching.